So I had number 21 from 3.6, and the directions are analyze and sketch a graph of the function, label any intercepts, relative extrema, points of inflection, and asymptotes. So the function was 3x to the fourth plus 4x to the third. And the first thing I noticed about it is that it's continuous because there isn't a denominator, which means there can't be any asymptotes or holes. So the second thing I did was find the x-intercepts, so I set the function equal to 0. So 3x to the fourth plus 4x to the third equals 0, and I was able to factor out a x to the third, so 0 equals x to the third times 3x plus 4. So I found that x was equal to 0 and x was equal to negative 4/3. So we know that there are two x-intercepts at the origin right here, and negative 4/3 0 right here. So then the next thing I did was find the y-intercepts, and you kind of already found it right here because this x-intercept at 0, 0 is also a y-intercept, but in case you wanted to double check, plug in 0 to the function, so when x equals 0, the function equals 0, and here you can see that there's a y-intercept. The fourth thing I did was find the relative extrema. So what you have to do is set the derivative of the function equal to 0. So the derivative of the function was 12x to the third plus 12x squared. I set that equal to 0, and I was able to factor out a 12x 12x squared. So 0 equals 12x squared times x plus 1, and so you find x to be equal to 0 and x to be equal to negative 1. And then to double check if those are really, if x equals 0 and x equals negative 1 actually have relative extrema at those points, you have to set up intervals. So I set up negative infinity to negative 1, negative 1 to 0, and 0 to infinity. So I plugged in a number on that interval of negative infinity to negative 1 into the derivative of the function, and I found that that was less than 0. The answer was less than 0, which means that f of x is decreasing on that interval. And then same for negative 1 to 0. I plugged in negative 1/2 because that is in between the interval into the function into the derivative of the function, and I found that was greater than 0. I'm sorry, that should be a greater than sign, which means that f of x is increasing. And then from 0 to infinity, I chose to plug in the point 1 into the derivative of the function. I found that answer was greater than 0 as well. So f of x is increasing here too. So because it is increasing on both of these intervals, we know that there's a flat line somewhere between x equals negative 1 and x equals 0. But we do know, because from the boundaries of negative infinity to negative 1 and negative 1 to 0, that the function changes from decreasing to increasing. We know that there's a relative minimum at negative 1, so you have to plug in negative 1 to the original function, and I found that f of negative 1 is equal to negative 1, so there's a relative minimum at negative 1, negative 1. And then the fifth thing and final thing I did was, and also the relative minimum you can find right here. You can see that that's definitely a minimum on this function. And then the fifth thing I did was find the points of inflection. So what you have to do is take the second derivative of the original function. So I started here. This is the first derivative of the original function, and then I took the derivative of that, found the second derivative to be equal to 36x squared plus 24x, and then I set that equal to 0, and I was able to factor out a 12x. So 0 equals 12x plus 3x plus 2. And I found x to be equal to 0 and x to be equal to negative 2/3. And then again, we have to verify that there are points of inflections at these two points. So I set up the intervals negative infinity and negative 2/3, negative 2/3 to 0, and 0 to infinity. So I plugged in a point in between on the interval of negative infinity to negative 2/3. I chose -1. I plugged it back into the second derivative, and I found that that answer was greater than 0. So we know that the original function is concaving up on that interval. On the interval negative 2/3 to 0, I plugged in a negative 1/2 into the second derivative and found that that answer was less than 0, so that means on that interval of negative 2/3 to 0, f of x is concaving down. And then on the interval 0 to infinity, I chose 1, and I found that the answer when I plugged 1 into the second derivative was greater than 0, and f of x is concaving up. So we have to then plug in negative 2/3 into the original function to find where that point is for the where the point is on in terms of a y. So I plugged in I plugged in negative 2/3 to f of x, and I found that that was equal to negative 48 over 81, which is roughly equal to negative 0.6. And then I plugged in 0 into the original function as well, and that was also equal to 0. So we have points of inflection at negative 2/3, negative 48 over 81, and the origin as well. So you can see that right here is a point of inflection. You can see it's concaving up from negative infinity to about 2/3, and then from 2/3 to 0, you can see that it's concaving down, and then the rest of the way it's concaving up after it hits the origin. And so the book says to verify with a graphing utility, and so I plugged it into a graphing calculator on the internet, and the graph that I sketched is roughly equal to, or roughly the same as this graph here.